Welcome back, strategists. Today, we are talking about perfect form and execution. Imagine a gymnast perfectly sticking a landing. Every single movement is calculated, deliberate, and flawless. That is exactly how you need to treat your Cambridge physics exams. Every sentence you write should be a graceful landing that scores maximum points. Today, we are tackling a monster topic from Syllabus 9702, alternating currents. We're going to look at the wild, untamed nature of the electricity surging through the walls of your house right now, and how we tame it. But more importantly, we're going to look at exactly how to answer exam questions on this topic. I want to introduce you to two students we see all the time. First, there's Alex. Alex overloads every answer with raw physics facts, but gives absolutely zero analysis. It's a total data dump. Then there's Sam. Sam rushes, panics, and completely misses the command word requirements in the question. By the end of this explainer, we are going to fix both of their mistakes and yours, transforming those red pen marks into green check marks. Let's get started.
Here is your exam mastery roadmap for today. We are going to conquer alternating current terminology, measuring AC power, half-wave rectification, full-wave rectification, smoothing the current, and finally, the key equations. But we aren't just going to memorize these. We are going to run them through our physics success blueprint so you know exactly how examiners want to see these concepts explained on your paper.
Section 1. Alternating current terminology. Now, before we look at the first concept, I need to reveal the strategy. The Cambridge assessment objectives are incredibly specific. They don't just want facts, they want structure. That's why top students use the Peel framework: point, evidence, explanation, link. Keep this framework in your head. Every time you see a high-mark question on AC circuits, I want you thinking point, evidence, explanation, link. Let's see how this applies to our first physics concept.
Up to this point in your 0625 or 9702 physics journey, you spent a massive amount of time with direct current, or DC. Think of DC from a battery as a steady, unchanging flow of water moving in exactly one direction. It is reliable. It is flat. Now, if an exam asks you to contrast direct current with alternating current, Sam will typically just write AC goes back and forth. 0 marks. Why? Because it lacks scientific precision. You need to explain that an alternating current changes direction continuously. Instead of just flowing in one direction, the actual charge carriers vibrate backwards and forwards in the circuit. That is your point and explanation in the PEL framework right there.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, look at these two graphs directly. This is a classic visual analysis question. On the left, direct current. It's just a horizontal line over time, steady, unmoving. On the right, alternating current from a simple generator. Look at the wave. The current rises to a peak, falls back through zero, goes completely negative, meaning it literally reverses direction entirely, and then comes back to zero again. This specific, graceful shape is known as a sinusoidal wave. When you describe this in an exam, do not just say it goes up and down, use the term sinusoidal. It shows the examiner you understand the underlying mathematical function.
Let's talk terminology. Because we are dealing with a wave, we use terms identical to what you learned in the oscillations topic. The frequency is the number of complete cycles of the alternating current per unit time. The period is the time taken for just one complete cycle. And crucially, we have the peak current, denoted as I0, which is the maximum amplitude of the current during the cycle. Now, Alex's trap here is writing down these definitions perfectly, but forgetting to link them. The link in our Peel framework means connecting the definition to the math. Because it's a sinusoidal wave, we can describe the current at any given moment with the equation I equals I0 times the sine of omega t. Always link your physical definitions to the mathematical model.
Section 2. Measuring AC power. This is where we see the biggest transformation, from red marks to green check marks. Let's look at a classic hurdle that trips up thousands of students every year.
Here is the critical problem, often presented as a multi-part question in Paper 4. If the current is continuously dropping to zero and spending half of its time flowing backwards as a negative value, how on earth do we calculate the power it generates? Sam usually panics here and guesses that the average power is zero because the positive and negative cancel out. No way. Think about the actual physics. Does the negative current mean negative power? Does a toaster suddenly absorb heat when the current reverses? Of course not. Let's rewrite this thought process.
Watch how the math brilliantly solves our physical problem. Take a look at the top graph showing the alternating current. It dips well below the axis into negative territory. But look at the bottom graph, representing power. It is strictly always positive. Why? Let's use our Peel framework. Point. Power is always positive. Evidence/explanation. Because the power generated by a current in a resistor is equal to the current squared times the resistance, I squared R. And as we know from basic math, the square of a negative number is always positive. Link. Therefore, even when the current flows backward, it is still dissipating power and generating heat. That is a flawless, full-mark answer. Notice also a key detail examiners love to test. The average or mean power generated over a complete cycle is exactly equal to half the peak power during that cycle.
Now, because the current and voltage are constantly changing, we need a standard way to compare an AC supply to a DC supply. Enter the RMS, or root mean square value. Listen closely, because this definition is an absolute goldmine for marks. The RMS value of an alternating current is defined as the value of steady, direct current that would produce thermal energy at the exact same rate in a resistor. Produce thermal energy at the exact same rate, that is the phrase that gets the mark. To find the RMS current mathematically, you simply take the peak current and divide it by the square root of 2. The exact same rule applies to voltage. RMS voltage equals the peak voltage divided by the square root of 2. It is our perfect way of creating a DC equivalent for an AC world.
Let's apply this to a real-world scenario that pops up in exams constantly. When a question states that the mains electricity from the wall is rated at 230 volts, that is actually the RMS voltage. It's the equivalent steady voltage. Now, if an exam asks you to calculate the peak voltage, apply our time management matrix. This is a 1 or 2 mark calculation. Do not spend 5 minutes on it. Just multiply the 230 VRMS by the square root of 2. You'll find that the true peak voltage of your wall socket is physically hitting about 325 volts during its cycle. The current swings all the way up to 325 volts and all the way down to negative 325 volts dozens of times a second. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's dive into Section 3, Half-Wave Rectification. Welcome to our interactive workshop. Get ready. While it's highly advantageous to transmit power across long distances using alternating current, the delicate microchips in your appliances require direct current. They just can't handle the constant reversing. We must convert the AC to DC. The simplest method is a single diode, shown in the top diagram. Challenge 1. Data scan. You have 60 seconds on the exam clock to extract the chord trend here. A diode acts like a one-way street for electrons. It allows current to pass only one way. When the input voltage tries to go in the opposite, negative direction, the diode completely blocks the current, meaning the potential difference across the resistor drops to exactly 0. Look at the graph below. We've successfully stopped the current from reversing, but we basically chopped the wave in half. This is half-wave rectification. Section 4. Full-wave rectification. Let's look at a much more elegant solution and a much more complex exam question. The glaring issue with half-wave rectification is that we are literally throwing away half of our power cycle. There is a current for only half a cycle. To fix this, engineers created the diode bridge. Now challenge 2, find the flaw. Sam wrote this in a mock exam. In a diode bridge, the current passes through all 4 diodes simultaneously to maintain a positive flow. Spot the flaw. It's completely wrong and loses all marks. Let's trace the actual path. Step 1, when top terminal P is positive, current flows out, passes through diode B, goes down through our resistor from left to right, and returns through diode D to point Q. Step 2. When the cycle reverses and P becomes negative, the current flows out of point Q, passes through diode C, and goes down through our resistor, again from left to right, returning through diode A. It only uses 2 diodes at a time.
Let's look at the examiner commentary on why this diode bridge is so brilliant. Juxtapose these 2 graphs. On the left, our old half-wave graph, full of dead, wasted space. On the right, the full-wave rectified output. Because the diode bridge ingeniously routes the current through the resistor in the exact same direction regardless of the input cycle, the negative half of the wave has essentially been flipped upwards into positive territory. We now have a strictly positive, continuous series of pulses. We aren't wasting any part of the cycle anymore. This visual comparison is a favorite for 4-mark explain questions, so burn these graphs into your memory.
Section 5, smoothing the current. We have positive voltage, but it's still way too bumpy.
The output from our full-wave rectifier is still dropping to 0 every half cycle. Sensitive electronics like your smartphone would crash instantly. We need a smoother direct current. To achieve this, we introduce a capacitor connected in parallel across the output resistor. Challenge 3. Speed writing. You have 30 seconds to write one perfect Peel paragraph explaining how this capacitor works. Go! Think of this capacitor as a temporary reservoir for electrical energy. Your paragraph needs to explain exactly what that reservoir is doing when the voltage fluctuates. Let's see if you got it right on the next slide.
Time's up. Here is the perfect, mark-winning explanation. As the input voltage rises to its peak, it charges the capacitor. But, and this is the crucial part, when the input voltage starts to fall away from its peak, the capacitor immediately starts to discharge through the resistor, essentially filling in the gaps of the voltage drop. Now here is a massive trap that Alex always falls into, forgetting the RC time constant. The RC time constant, resistance multiplied by capacitance, must be much greater than the time period of the original AC input. Because the time constant is so large, the capacitor just does not have sufficient time to discharge significantly before the next wave pulse tops it up again. The result? Instead of crashing to 0, our voltage stays high, showing only a slight variation known as a ripple. That is your flawless Peel answer.
Section 6, Must-Learn Equations. Let's finalize our Cambridge physics system.
Here is your ultimate cheat sheet graphic. To reach that 100% mark potential, you need to apply our 3 rules: command word decoding, Peel framework application, and the time management matrix. These equations are the tools you'll manage your time with. First, the sinusoidal wave equations. I equals I0 times sine omega t, and V equals V0 times sine omega t. Second, the crucial conversions. RMS current equals peak current divided by root 2, and RMS voltage equals peak voltage divided by root 2. When you decode a command word like calculate, grab these tools immediately. Don't waste time deriving them. Know them instantly so you can spend your time on the complex explain questions.
We've covered a massive journey today, from chaotic, vibrating charges all the way to a smooth, flat, direct current. And we've built a system to guarantee top marks while doing it. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. And before you go, I'll leave you with a final thought to test your new knowledge. Knowing how AC is rectified and smoothed using components with physical resistance, why exactly does your laptop charger still get so warm when plugged into the wall? Think about the energy dissipation. Until next time, keep analyzing, keep practicing, and perfect that exam form.